Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the Leetcode 75 list on blind. The problem that I'll be working on today is problem 100. It's called same tree, and it involves again binary trees. So let's read the problem statement and a little bit of the given code in a bit. So given the roots of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. Example 1. Okay, we can see that these are equal, so that's true. Example 2, these are not equal because this 2 is the left child and this 2 is the right child. In example 3, these are not the same because once again the left and the right child are switched. Okay, the number of nodes in both trees is in the range 0 to 100. Great. So I guess here we have a binary tree, and each node has a value parameter, and then it has a left and a right symbolizing the children. And we are given a method with P and Q, where P and Q are the two different trees. Great. So I guess in order to solve this problem, we need to establish the recurrence relations, just like we've done in other problems that involve recursion. So let's get started with the base cases. So one that we can think of right away is if both of the trees are empty, meaning that P and Q are null, then they're obviously the same. So that's something that's if P is equal to none and Q is equal to none, then this will be true in any case. Now, another thing is, when will this not be true? So for instance, if the current value is not the same at one node, then obviously the trees are not the same. Therefore, if P dot, so I guess another thing that we'll have to check first is if one of the trees is null and the other one isn't null, then this will obviously be false because we will be exploring a node that exists on one tree but doesn't exist on another, since we're going to traverse them the same way. We're going to traverse both always to the left or always to the right. But every tree, when we traverse them, we're going to go always in the same direction for both trees. So in order to avoid any sort of problems when accessing the val variable, we're going to check first if P is none and Q isn't, and vice versa, just to make sure that we cover all the cases where P and Q can be none, so that we can always access this parameter right here and we don't get any errors. So if P is equal to none and Q does not equal to none, and while this does not really matter because, as we know in Boolean logic, the ands kind of like make it such that the statement that is anded is in parentheses. I'll still write it down just for the sake of clarity. So if this is the case or this is the case, then obviously this will be false. And we're not done with the base case. We're going to add a couple more, so don't worry too much about that. Or if P dot value does not equal Q dot value, then this is false. So far we have those three base cases in which we return false. Now, we are, like I said before, when we traverse the trees, for example, right, since we're going to check if they're structurally similar, in order to determine that this tree isn't the same as this, when we traverse on this tree, the left, we're going to do the same thing on this tree. We're going to go to the left. And if the left subtree and the right subtree and the current node is equal for both trees, then that means that those subtrees are equal. So let me repeat myself just to be a little bit more clear. At any point in the tree, we're going to have a subtree. So this subtree right here, right, is just a subtree that has one node. So a subtree is equal to the corresponding subtree if their left and right children are the same, and if their current nodes are the same as well. Else, they're not the same. So let's write it down as a recursive statement. So the first thing that we know is this. We know that left tree is equal to self is same tree, p dot left, and then q dot left, and then right tree is equal to self dot is same tree, p dot right, q dot right. So this will take care of traversing the tree. As we can see, we explore the right subtree and the left subtree of the current node. And after that, what we have to say is if p dot value is equal to q dot value, and we're always going to be able to access this variable because, like I said before, we have covered all the cases in which p and q are none. Therefore, we will never run into these sort of errors where we're going to be like, oh, p dot value does not exist because p is null, and similarly for q, because these are all the cases in which that can happen. So if p dot value is equal to q dot value, right, if the nodes have the same value, so this covers that, and left tree is equal to true, and right tree is equal to true, then we return true. Else, we return false. And that should cover all the cases. So let's try with example 1, example 2, and example 3, and then we submit it. So here we start with 1 and 1. So p is not none and q is not none, so we go past this. This is not true, this is not true, and this is not true, so we ignore this as well. So for both p and q, we're going to enter line 18 here, and we say left tree is equal to this, so we access this node and this node. Now we're in left tree, and similarly, this is, we skip this and we skip this, and then we go on left tree and right tree for both this node and this node. We can see that it's pretty evident that for both the left and the right child of these nodes, since they are null, we will always access this statement right here, statement 14. So that means that left tree and right tree for both of these return true. And if p dot val is equal to q dot val, in this case they do, that means that these two nodes are true. So the left subtree of this node 1 is equal to the left subtree of this node right here, because when we bubble up, well, we'll see later, I guess we haven't accessed that. Now we check the right tree for node 1 again. So we check this right tree and this one right here. Again, like we did for 2, we call is same tree on p dot left and q dot left, and p dot right and q dot right for these two. They both have null children, so they return true, and their values are the same, line 20. Therefore, the left subtree and the right subtree, for this node and this node are the same. So now for this node right here, left tree and right tree equal to true. Now, p dot val is 1 and q dot val is 1. As we said, left tree is equal to true and right tree is equal to true. So we return true. In another case, we would return false, but that's not the case. So that example 1 checks out. Let's see example 2. So in example 2, we start at the root. This is not true, and this is not true either. So now we go to line 18, and then we call is same tree on p dot left. So here we enter this node right here, and here we enter a null node. So in this case, P is this node 2, and Q is equal to none. So statement on line 14 is not true, but this right here, P is not equal to none and Q is equal to none, is true. So we return false. So for these roots, left tree is equal to false. Similarly, for the right subtree, this one is null and this one is not null. So in this case, P is not null and P is null and Q is not null. So right tree is also false. Therefore, left tree and right subtree for these nodes is equal to false. And the statement right here will not be true, so we are going to return false. And in example 3, we do the same thing. We check these two. Both their left and right subtrees are the same because they have no children. However, p.val and q.val for these two is not the same. So the left subtree for these two nodes, the variable left tree, will be equal to false. And similarly for the variable right tree. So let's test the code. It's probably a little bit of a connection issue, but as you can see, it's a deficient solution. Depends a little bit, like I said on previous videos, about like when you submit it, but you guys have plenty of experience with this kind of stuff. So yeah, as you can see, this solution is a O of n solution in runtime, and that is because we have to traverse. Actually, in the worst case scenario, it's going to be an O of n plus m runtime, where n is the size of one tree and m is the size of another tree. In the worst case scenario, they're not the same and they have different sizes, so we have to take that into account. And the space-time complexity at any point is going to be O of max n and m. Yeah. So, and the reason why that is because in the worst case scenario, like both of the trees, like I mentioned before, when we do these recursive calls, right, we have a tree that only has one child per node, except the last one, which is childless. And in that case, we will always go as deep as we can on the recursion. Therefore, actually, it would be a space-time complexity of O of the minimum of n or m, because at some point, whenever we reach the furthest down we can for one of the trees, and the worst case scenario for height is like every single node is consecutive, so that's the worst case scenario for the height of a tree. In that case, what will happen is that once we reach the node with the lowest height, we're going to reach a null pointer, and then we enter this statement right here, 16, and we're not going to go further on the node on the tree that has the furthest depth. So the space-time complexity is going to be a big O of the minimum between n and m, but you can also say the height of tree P and the height of tree Q. And like I said, the runtime is big O of n plus m. I know this last space-time and runtime complexity was a little bit difficult, so if you want to, just make sure to replay it and try and make sense of it. But yes, that's the end of the video. I hope you enjoyed it and that it was helpful, and I'll see you in the next one. Bye-bye.